will talk about quantum error correction.
Yeah, hi. I'd like to thank the organizers for the invitation. It's great to be in India, my first time. Uh, Enjoying everything so far. So indeed, today I'm going to talk about a recently proposed connection between the emergence of bulk locality in the AdS CFT correspondence and the theory of quantum error correction. Um, so yeah, let's just put this in context, right? So AdS CFT is supposed to give a non-perturbative definition of quantum gravity. That's exciting. It deserves an exclamation mark. Um, and so far, the way that we usually understand that is the quantum statement of the duality goes through the state operator correspondence, right? We say, we use, low dimension operators correspond to perturbative excitations of the vacuum. High dimension operators create big black holes. Um, and, this way of phrasing it is, of course, very powerful because it lets you use a lot of the machinery of conformal field theory, operator product expansions and so on. What I'd like it to talk about today, however, though, is trying to understand the duality at a fixed time in the Schrodinger representation of the state, which is not how people which is different than this, right? So I'm not going to go put things at the bottom of the Euclidean sphere and so on. I want to talk about the state, right at t equals 0. And I just want to make an ideological comment that I mean this is essential if we want to understand the relevance of entanglement for the emergence of the bulk, right? I mean entanglement is a property of the state at a fixed time. So we'll see that formulating AdS CFT this way is going to lead to some perhaps surprising consequences. And these consequences can be naturally understood using this language of quantum error correction, which I assume is unfamiliar to most people in the audience. So I'll explain it when I get to it. And this is mostly going to be based on this paper with Ahmed Almiri and Shidong. And then maybe at the end I'll talk a little bit about a sort of exactly soluble model that illustrates the general conceptual things that were explained in this paper. So along the way, just to give you the big picture first, we'll do a couple of things which I think are interesting. So we can quantify the sort of intuitive relationship between the radial direction and the bulk and the scale and the CFT. And I'll do that by recasting it as a statement about how well protected quantum information in various places in the bulk is from erasing subregions of the boundary. I'll also clarify this precursor question, which was discussed by these people back in the late 90s, emphasizing that the thing that's really essential for the emergence of bulk locality and causality is the long-range entanglement of low-energy states in the CFT, not the presence of gauge invariance in the CFT, which is what these people had in mind. I will also reinterpret the holographic entropy bound as a consistency condition for the success of quantum error correction. And then finally, although it'll be fast, I'll introduce a discrete model of AdS CFT, which is exactly soluble and which illustrates most of the things that I said. So altogether, I think this gives a new and I think probably more precise understanding of how holography is working in the AdS CFT correspondence. So hopefully I'll convey you some flavor of this. Obviously in 25 minutes there's a limit to how much I'll be able to convey. Okay, so let's first recall some basic properties of AdS CFT, right? So it's a quantum duality, so there's an isomorphism between the Hilbert spaces. Any state in the CFT is supposed to have a bulk interpretation, and vice versa, although I guess since I'm thinking of it as a definition, it's more going from the CFT to the bulk. So then, things like the Hamiltonians, the generators of the AdS symmetries, right, those are going to be equivalent. But then the thing that really gives the meat to the duality is this piece of the dictionary, which is sometimes called the extrapolate dictionary. I guess Douglas and I made that up. Which says that if I take a bulk field and I extrapolate it to the boundary, so R going to infinity is the boundary here, I get a local primary operator in the CFT of some definite scaling dimension. Okay. Now, I mean, that's great in terms of thinking about boundary correlators, but if we want to think about what's going on directly in the bulk, then we'd like to try and understand to what extent can we back off of this limit and make sense of this object phi at a finite point in the bulk. Can we still think of that as an operator in the CFT? Certainly in perturbative perturbative quantum gravity, it's an operator on the gauge invariant Hilbert space of states. Now, there are sort of standard complaints, which I'm sure probably most of you are already thinking about trying to do this, so let's get them out in the open. So the first one is that in a diffeomorphism invariant theory, there of course are no gauge invariant local operators, so phi shouldn't exist. Okay. This is of course true, but you can easily deal with this by just being a little bit more careful about gauge fixing. And it means that the operators won't quite really be local, in the same way that in electrodynamics, charged fields have to be dressed by Wilson lines to make them gauge invariant. But nothing I say is really affected by that too much, so I'm not going to discuss it explicitly unless I'm bothered about it in the questions. Now, there's a more serious objection, however, which we are going to have to take seriously, which is that we know from black holes that entropies go like areas, not like volumes. That's eventually going to have to put a limit on trying to have a volume's worth of commuting operators in the bulk. I mean that's the point that led to holography in the first place. But the approach I'm going to take is I'm just going to ignore it for as long as I can, and I can see how far I go before I get into trouble. Now, it will mean, though, that I'm in the end trying to define what I'm going to be saying is approximate. I'm going to be constructing approximate bulk operators in the CFT to reproduce the approximate concept of bulk locality. Okay. Now, in fact, this is 2015. This is not the first time someone asked this question. There's a long literature on this subject. So there's a strategy in perturbation theory of exactly constructing these operators. So what you do is you look for a CFT operator phi, which obeys the bulk equations of motion as an operator equation, and is consistent with the extrapolate dictionary. So it obeys these boundary conditions. Okay, and then that's some PDE. We're solving it. It's an operator PDE. We're solving it with some boundary conditions, and we can hope to solve it at least perturbatively order by order in 1 over n. And that has been explained by, this is some subset of the papers, which I particularly like, which explains how to do that. So the upshot is that this leads to formulas like this, where you say phi of x is equal to the integral of some, the operator O, which is dual to phi, times some function k, which is called the smearing function. It's not the bulk boundary to boundary propagator, which is the confusion people sometimes have. And then there's a series of order 1 of 1 over n corrections to this formula. And so I mean, this k, right, it does the obvious thing. It obeys the free wave equation in x, and it becomes a delta function as little x goes to big X. So and then this R is some region in the boundary. So for simplicity, I've done the Poincare version here, right? So X is some operator in the Poincare patch, and then I'm doing this integral over this green region R on the boundary. This is often called global reconstruction because this constructs an operator in the CFT where if I evolve it back to an operator at fixed time here, it involves all points on the boundary. So it requires the full a sphere of the CFT to represent this operator. Okay, so global reconstruction. Now I'll just very briefly mention the 1 over n corrections. There's some diagrams you can use to compute them. They're important in understanding how back reaction is included, right? Like if you put in a planet or something, then you have to resum some subclass of these diagrams to see how this k gets corrected. And just to make fun of the next speaker briefly, so I'll say this is not what's sometimes called state dependence, and it's quite consistent with the linearity of quantum mechanics. Okay, so far you can, I mean, this procedure though, it seems almost too good to be true because you're just solving some PDE. You can do it for any equations of motion, even the wrong equations of motion. You just make up some bulk equations of motion that have nothing to do with the right ones, and you can solve these equations. But that clearly you shouldn't do that. That's stupid. Why? I mean, what goes wrong if you do that? Oh, and I guess maybe just to add, sometimes people get confused about how you know the right ones. So you read this paper, and that tells you how to know what the right ones are. Now, an example of something that would go wrong is you can look at the algebra of these operators, right? So you can look at, say, the commutator of phi of x and phi of y at space-like separation. And that should be 0 in the bulk, but it won't be true in the CFT unless you use the right equations of motion in constructing these phis. So that's explained in paper by these people. Now, I want to emphasize, though, that what they did was they checked this in sort of in correlation functions with an order 1 number of phis. So that's different than saying that these guys actually commute as operators in the CFT. It only says that the commutator is 0 within some small set of states. And that's actually important. So this ends the review part of the talk. So in fact, there's a simple argument that says that this kind of commutator can't actually vanish or even be small as an operator equation in the conformal field theory. So let me explain that. So indeed, let's first recall, of course, that in quantum field theory, so here when I use capital letters, I mean boundary points. So if you have two boundary operators, local operators, at space-like separation, they commute. If we know anything, we know that. And that's how locality is implemented. But we could ask, in the bulk, right? Say phi of x is one of these guys sitting in the center of the bulk on some Cauchy slice, and O of x is some boundary operator, which is living on the boundary Cauchy surface, which is the boundary of the bulk Cauchy surface. Just some arbitrary local boundary operator. So you could ask, do we have that phi and O commute? Well, in the bulk, they're space-like separated, so you might think that they do. But that's wrong. Actually, they can't. They can't even close to commute. Why not? Well, it's inconsistent with the standard property of quantum field theory, which is called the time slice axiom. Here's the formal statement, which you can read about in Streeter and Whiteman, which I embarrassingly have been reading too much of recently. Or in Hogg, actually, these sort of axiomatic guys. Intuitively, it's just saying that the algebra of local operators on a fixed time slice in a quantum field theory acts irreducibly on the Hilbert space. So then, by Schur's lemma, anything that commutes with all the local operators has to be a trivial operator proportional to the identity. So that says we can't have this, right? Because this phi of x is something which we kind of might want to naively commute with all the local operators. So this is interesting, right? It tells us that the bulk algebra, that the algebra of bulk operators cannot be realized at the level of the operator algebra in the CFT. Or maybe more colloquially, unlike boundary causality, bulk causality is not an operator equation in the CFT. Okay, but then how do we express it? And more generally, how do we think about the emergence of the bulk algebra? It's got to be true in some sense. Okay. Now, I can sharpen this paradox by introducing one more tool, which is called the AdS Rindler Reconstruction. So previously we talked about the global reconstruction, where we, given some bulk operator, we reconstructed it on the entire boundary at a fixed time. The AdS Rindler Reconstruction, it proceeds along the same lines, but it allows you to reconstruct it only on a subregion. And so, I won't define the symbols in detail, but given any boundary subregion such as A, this A here, I can construct a bulk region W of A, where any operator in that bulk region, which I guess that bulk region is usually called the causal wedge, it has some representation in the CFT with support only on A, so only on the subregion. And in the bulk, it's equivalent to the global reconstruction. It's just some Bog-Lubov transformation. Now, it's more intuitive from above, right? So now I'm looking down on that slice. Here's the subregion A. And so this operator phi of x can be represented in A because it's in this red causal wedge. But this operator phi of y cannot be represented in A. And in fact, it can be represented in the complement of A. So this is a fairly precise realization of this older idea of subregion duality, which you can read about in these papers. Okay, now we can use this to sharpen the commutator paradox, right? So say O of x is your favorite local operator on the boundary here. Well, and phi is my bulk operator here. Well, I can make some representation for it by taking this boundary region, where I just drill a little hole around it. And now it has some representation just on the boundary of the red region. Well, that representation is obviously going to commute with O because they're space-like separated in the CFT. But similarly, say instead your favorite local operator was here, well then there's some other representation of this operator which is obviously going to commute with that one. So we can always find, for any O, we can always find some reconstruction of phi where it really does commute with O, exactly, not plus up to e to minus n squared or something, but really exactly commutes. This can only be consistent with the time slice axiom if these different representations of phi on different subregions aren't actually all the same operator in the CFT, right? Otherwise it would be inconsistent with the time slice axiom. So here's another illustration of this kind of thing. It's my favorite one. So now say we split the boundary into three regions, A, B, and C, and we look at some bulk operator sitting in the center here. So now we're in this interesting situation where, so the phi of x sitting here, right, it has no representation on either A, B, or C, but it has a representation either on A union B, or B union C, or A union C. So that's a little bizarre, right? I mean, where is the quantum information? You know, if there's some spin there and it's in some state, it seems I can access that information, you know, from any one of these regions, but you know, from their intersections, no. So okay, so something interesting, you know, is going on here. Okay, but what is it? All right, so I claim it's quantum error correction. So let me tell you what that is, and then hopefully it'll be obvious to you also that it's quantum error correction. Okay, so what is quantum error correction, right? Say I want to send you some quantum state in the mail, but I'm worried that it might get lost. So, you know, if it were a classical system, right, I can just send you 100 copies of the state, and, you know, I just copy the state 100 times, send you 100 copies, and then even if, you know, a quarter of them get screwed up, so what? You can do majority rule and still figure out what the state is. But in quantum mechanics, I can't do that, right, because of the no cloning theorem, so I can't clone the state. But there's still a way of doing this. There's still a way for me to send you the state in such a way that even if you lose part of it, you can still recover the quantum information. And you know, just historical comment, right? I mean, this was developed by people who are trying to make quantum computers because obviously they want to preserve the memory against decoherence. So, you know, despite the no cloning theorem, the basic idea is still you want to embed the state in a larger Hilbert space. So let me just give an example so that we can see how this works. So say the state I want to send you is a single qubit state, right? So a qubit is a 3-state qubit. So this is just some state in a 3-dimensional Hilbert space. So the idea is instead of sending you just this state, right? If I send you this state, maybe it gets lost and that's it, right? So that's not very well protected at all. So the idea is I instead send you 3 qubits in this state. So this I tilde now is a basis for a special 3-dimensional subspace of the full 27-dimensional Hilbert space of 3 qubits. So whenever I put a tilde here, I'm talking about a 3 qubit state. And this subspace is called the code subspace. Now, okay, what does that buy us? Well, we've got to pick a subspace to see. Here's a subspace. So here's a good subspace to choose. There's 3 states in the 3 qubit Hilbert space. Why did I pick this one? Well, it's very symmetric between all 3 of the qubits, and each one of these states is very entangled. In fact, they're so entangled that for any state in the subspace spanned by these guys, the density matrix on any one of the qubits is maximally mixed. So it's just given by this. So any one of the qubits has no information whatsoever about which state in the subspace that we have. And so that should be somewhat reminiscent to what I was saying before. Right, no information about the encoded state. So, and in fact, this leads to the somewhat, well, I find remarkable fact that we can completely recover the quantum state from any 2 of the qubits. Okay, so how does that work? Well, here's some unitary transformation. I guess homework problem to find it. So I claim this unitary transformation has the property that if I act on any one of these basis states, then I just put the state, the I, back onto the first qubit, and then I get some state on the second 2, which is independent of the state, of the I here. Homework problem, see that that's true. It is. So then we have this remarkable fact, right? So say I send you this state psi tilde, the 3rd qubit gets lost in the mail. You know, you don't have it anymore, but you've got your quantum computer, and so you take the first 2 qubits, you act on them with this U12, and hey, look, now you've got the state back on the first qubit. Okay, and clearly, since this was totally symmetric, there's also going to be a U23 or a U13. So by doing this, I can restore the state on any 2 of the qubits. Okay, so that's how quantum error correction works. Now, it's reminiscent of this ABC example I had, where the boundary had 3 regions, right? And I could reconstruct the bulk operator on any 2 of the regions, but not quite the same. There I was talking about an operator. Here I'm talking about states. We can flip it though, right? So say O is some operator that acts in the single qubit Hilbert space. So we can always find some 3 qubit operator O tilde that implements it on the code subspace, just the same transformation, right, with the same matrix elements, but now a 3 qubit operator. Generically, that operator will not have non-trivial support on, it'll have support on all 3 of the qubits, but using U12, for example, I can come up with an operator that implements this O that acts just on the first 2, okay? And similarly, by symmetry, I can do also 1-3 and 2-3. So now this is exactly like this, right? I mean, I have this subspace. The transformations on that subspace can be implemented either using operators on 1-2, 1-3, or 2-3. It's really now the same as this AB, BC, and AC. So you see, by using the entanglement of the code subspace, we can just reproduce one of these paradoxical properties that we derived from the AdS Rindler reconstruction. We can also make contact with the commutator, right? So the commutator puzzles, right? So say x3 is some operator on the third qubit. So that's like a local boundary operator. And then these phi tilde, psi tilde are arbitrary states in the code subspace. Then we can look at the commutator of this with one of these operators that acts within the code subspace. Now, since this O tilde is always acting to the left or the right on a state in the code subspace, I can replace it by this O12, which represents that operator acting only on 1 and 2. But now it's going to commute with x3 because it's just defined on different qubits. So you see we can resolve the commutator puzzle too. We can get something that commutes with all of the local operators without being a trivial operator. So this is the lesson for AdS CFT, is that the algebra of bulk operators, it holds only on a subspace of states in the CFT, and moreover the subspace has to be highly entangled from the point of view of the local CFT degrees of freedom at a fixed time. Okay, we're seeing here really that the entanglement is essential for that, just to reproduce basic properties of local bulk physics, even before we talk about black holes or anything like that. Okay, now we can try and make more direct contact with AdS CFT. We're going to need to generalize this. I obviously don't have time to tell you the whole general theory of quantum error correcting codes, but it does exist. They're necessary and sufficient conditions for when the analog of this U12 exists. The only thing I'll tell you about it is that there's a rule of thumb, right? So say you have n total qubits. I'll just switch back to qubits. You want to protect a k-qubit message from the eraser of L or fewer of the qubits. So that's just some sort of generalization of the problem we just discussed. Then this is a good condition. So basically, if you want to send a bigger message or you want to protect against larger erasures, then you need more total qubits. Okay, that's very, very intuitive. Now, I also don't have time to explain how I can, what exactly the map of symbols is to turn this into AdS CFT, but I'll just show you I'll sketch how you can see this kind of inequality in AdS CFT. So for simplicity, right, we can just pick the code subspace to be spanned by states where you act on the ground state of anti-de Sitter space with at most k local operators within some region in the bulk whose size is of order the AdS radius. So then you can estimate how big the number of qubits is that you need that's relevant here. It's basically n squared because only the zero modes of the matrices are relevant. Here I'm talking about n equals 4. And so if k is order 1, then what this inequality tells us is we just need more than half of the qubits. Okay? And that's right. That's what the Rindler reconstruction told us too, right? It said for this guy in the center, if I had more than half of the boundary, I could fit this in the causal wedge. If I had less than half, I couldn't. But you see, so that's for the center, right? But then you see as we go away from the center, the protection gets less good, right? So this is protected against any one of these large green erasures. But this guy over here, right, the one near the boundary, well, even this tiny red erasure is enough to destroy the information. So indeed, you see that sort of the radial direction is sort of related to how well protected the information is. And we can be more precise about that. We don't have time. Now we can ramp up k. We can ask sort of how many operators can I act with before I break the emergence of bulk locality. So clearly, it's not going to change until k becomes of order n squared, right? Until it does, this inequality is just going to work the same as before. But when it's of order n squared, that's just when we expect a black hole to form. So you see, we've recovered the holographic bound, right? The limitation on how much stuff you can cram into the center. But we've recovered it purely on the CFT side by using these inequalities of quantum error correction. Now, I learned actually this week that this can actually be saturated even in fairly domestic situations. Okay. So now I'll just 1 minute tell you about this discrete model. So this was some cartoon. It's quantitatively consistent with, as far as I can tell, everything we know about the CFT and the AdS. But can we really check it in detail? Well, that's hard in the CFT, but with these people, happy, I guess I'm HA, we found an explicit model of an actual set of error correcting codes that implement all of this. So I think it's based on tensor networks, which Bartek explained. I think I'll just show you some pictures. So these are what the codes look like. You have this is the tensor network. Each of these red dots is a tensor. By choosing them carefully, you can arrange to get so you have a spin chain on the boundary. You have some code subspace of states where you can describe all of these bulk excitations, and you can see that they have this reconstruction on a subregion of the boundary property, right? So like this green operator here is reconstructed on a small region. This blue one is reconstructed on a bigger one. And these arrows, which I didn't explain, you can kind of send whichever way you want. So I could have also reconstructed it on this region. So it gives a full boundary realization of the bulk algebra on a subspace of states. It also has black holes. That accounts for the rest of the Hilbert space. And you know, there are many things it doesn't have. Obviously, it's just some toy model. It's not the full theory. But I think it does illustrate the error-correcting properties of AdS CFT quite clearly. You know, these are new codes. That's interesting. So maybe they're good for something. You know, maybe when you have a cell phone quantum computer 30 years from now, it'll be the reason it'll work is because it's simulating quantum gravity in AdS CFT. That would be an engineering application for quantum gravity. So yeah, I think I'll stop there. Thanks for listening. Yeah.
Questions?
So you refer to the algebra of operators acting on a subspace of states. Is there a notion of a representative of a state in this subspace acting on which with simple operators I can generate the entire subspace?
Yeah. So in the way that I like to think about it, you pick some. So these subspaces aren't unique. You pick them sort of based on what you're interested in. But I think the best way to describe them is indeed you pick some state in the CFT which has a semi-classical description in the bulk, and then you consider acting on it with these local operators in the bulk, and then the subspace is defined as the linear span. So indeed that's how I like to think about it. Yeah.
Yeah. So I have two questions. First one is you spoke about how the AdS Hilbert space only reconstructs a particular subspace of the CFT Hilbert space.
No, to be more clear, good. So all states in the CFT have bulk interpretations, but not all of them have bulk interpretations that don't have any black holes in them. So this is something which I didn't have time to explain in detail. But the question of how you get out of the subspace involves forming black holes. So we saw the holographic bound was relevant there. Essentially, this allows you to describe operators as long as they're outside of the horizons of black holes. Yeah.
Okay, so
perhaps a little bit inside.
Yeah. Okay, so second question I have. So today in Bartek Czech's talk, he showed a completely different construction where he's constructing something from a CFT which is not AdS.
Yeah.
And are these two constructions related in some way?
It's not clear. So Bartek and I are trying to do different things. Bartek is starting with Mira and then trying to come up with a way of interpreting that in the CFT, which is consistent with Mira. I want to start with bulk physics and then try and think of a tensor network which is describing the actual geometry. So for these models, which was not Mira. So I didn't really explain, but these tensor networks are not Mira. And actually Mira doesn't have, for example, these error correction properties. So if you wanted, the way I would describe it is if you want to interpret the tensor network, if you want to interpret a tensor network as a model of a bulk geometry, you shouldn't use Mira. You should use these instead. And now but that doesn't mean that Mira isn't good for something. And so I think what Bartek is doing is sort of coming up with something that Mira is good for. Yeah. I don't know if Bartek is still here. He might disagree with that.
Okay, last question.
There was a paper by Polchinski and collaborators which interpreted your phenomenon in terms of gauge, operators in different gauges or something like that.
Yeah, yeah.
Do you have a comment on that?
Yeah. So we had several months of discussions about that. They now agree with me.
That's a lovely answer. So let's thank the speaker.